section 3.7 on higher derivatives. Section 3.7 on higher derivatives is basically an empty section. There's almost no ideas in this other than the idea that you can take the derivative of a derivative. Okay, that's it, right? That it is legal to try to take the derivative of a derivative. Right? And if it happens, then you can take that second derivative, and you have something called the second derivative. You can take the derivative of that. It's called the third derivative, and so on and so forth. Okay, so not really much to this. Maybe the thing to notice, is that there's a notation, right? So the Newtonian notation, to take one derivative, you say f prime, right? Take the second to take the. If I write f double prime, what that means is that you've taken the derivative and then you take the derivative of that. Okay, so right, the derivative of the first derivative is denoted by this f with two primes on it. Second derivative, right? That is second derivative, right? And if I had a lot of primes here, right, that would be however many, and that would be the sixth derivative of f. Okay. But normally when you have a lot of primes, you don't just put a bunch of primes there. You put a number in. You put a number in parentheses. So this is usually used. This is used to denote the sixth derivative, right? F superscript parentheses 6. Okay, right? Or the nth derivative for some number n. Other notations for this. Some people write. This is pretty common. You write something like this: dk f dx k. What this really is you're taking the derivative k times of f, and that's probably a clearer notation. That you take an f and you do the derivative k times on it. But for some reason, people use this notation also, which I don't like as much. But it just means this. Okay? Just all these things mean the same thing. Take the k derivative. I should call this k. K is the same thing as this. Same thing as this. Sometimes use a big D, just like big D, K. All these things are just notation for taking the derivative K times. Okay, and that's basically it. There are some physical interpretations, right? If f is say position at time t on a straight track, on a straight track, then f prime is the velocity, right? Is the instantaneous velocity, velocity, and then f double prime is the instantaneous acceleration. Right. Acceleration. Yeah, the instantaneous rate of change of the velocity, and so that's the acceleration, and so on and so forth. But like I said, there's not too much in this section. Some of the problems will be like, take the, calculate the. Let's do it. Okay, so here's one problem. It's basically an exercise in your rules of differentiation. Okay, so I guess it's good review. So here's one. So k of x is sine of x cubed minus 3x, and they ask for the third derivative of that. Let's just do the second derivative. That'll be instructive. That'll be sufficiently instructive. Okay. So take 1 minute and determine the second derivative. So take the first derivative and then take the derivative of that. Anybody want to say what they got or say how to do it? Luke, you looked up first. Do you want to tell me how to do it? Tell me like what you're using. What do you use to differentiate this?
So first I did sine outside of the I differentiated sine to be like sine x3 minus 3x times 3x squared minus 3.
Great, perfect. So you're using the chain rule.
Yeah,
right? Chain rule. So you say, well, I'm going to differentiate the outside guy, evaluate it at the inside guy, and then multiply that by the derivative of the inside guy. Great. And then take the second derivative.
Yeah, so then it would be negative sine. Oh, would you have to do the chain rule like twice? Oh, so it would be negative sine x3 minus 3x times 3x squared minus 3 times 2x minus 0.
So so you use the chain rule on this guy.
Yeah.
Why do you get the 2x minus 0? Why does the 2x minus 0?
Because don't you have to differentiate the 3x squared minus 3 as well? Or no?
No.
That would just stay the same.
Yeah. So remember, when you differentiate a composition, right, you take you just take f prime with g of x times g prime x.
Okay.
So I think so. So what you just did was you differentiated the first guy.
Yeah.
Okay. And so you have this you have two functions here, right?
Yeah.
One function times another function, and so you're going to use what kind of rule? We use
the product.
The product rule, right? So when you differentiate one function times another function, you get the derivative of the first guy times the second guy. Well, the second guy is this, right? Times that plus what?
Times that.
Right. So the first guy times the derivative of the second guy. So let's add those guys on. So the first guy times the derivative of the second guy. And what's that? What's the derivative of the second guy?
2x.
Don't forget the 3. 6x. Okay. So use the product rule. Use the product rule on this thing. You see that this thing is a product. You use product rule, and and then in the course of using the product rule, you realize you have to use the chain rule. Yeah, no.
Why is 3x squared minus 3 multiplied twice?
Yeah, so when we did the chain rule, right, so we took the derivative of this guy times the second guy, right? The derivative of the first guy times the second guy. This is the second guy. But we also had to differentiate this, right? And how do you differentiate this? By the chain rule. So you say the derivative of the outside guy evaluated the inside guy times the derivative of the inside guy, right? So when you differentiate this thing, right, this thing here, this part here is the derivative of cosine x cubed minus 3x, right? And then this thing here is just 3x squared minus 3. So the derivative of the first guy times the second guy plus the first guy times the derivative of the second guy. So the chain rule, because you use the chain rule, you need to multiply by the derivative of the inside guy. Any questions? Any questions? Isaac, yeah.
You mentioned that what's it called for the No, I'm not talking about the string, I mean like the notation on the other side. The right side of the board, I'm sorry.
Okay. Yes.
You mentioned that this position is instantaneous velocity and instantaneous acceleration.
Yeah.
It's like the first, that's
In physics, yeah, that's so like in a basic physics course, these are things that you would encounter. It's true that people have names for subsequent derivatives, but they're sort of not as commonly used. Like number 3 is called the jerk or something like that, like the instantaneous rate of change of the acceleration, the jerk. Number 4, I don't know. There's some name for it, but people don't. I think it's because just because human beings don't really, you may be conscious of an acceleration, right? But you're accelerating, and then your acceleration changes, right? But I don't think that people really have a good way of feeling things beyond that, and maybe that's why we don't have words for them. Okay. So here is maybe the hardest sort of problem that you might encounter. Say p of x is a degree 2 polynomial, and that p at time 0 is 2, p prime at time 0 is 4, and p double prime at 0 is, say, -7. What can you say or determine about the polynomial? Okay. So you have a degree 2 polynomial, right? It's like ax squared plus bx plus c, right? And here's 3 facts about it, right? Here's 3 facts about it. That at time 0, the position is 2, the velocity is 4, and the acceleration is -7. What does that tell you about p itself? Okay, so think about this for a minute, 2. See if you can say anything at all. Oh, so p is a degree 2 polynomial. It's a quadratic form polynomial, so it's going to look like this, right? You don't know what a, b, and c are. A, b, and c are some numbers, right? But it's p looks like that. You don't know what a, b, and c are. It's a quadratic polynomial. You done? Okay. so talk to somebody for a minute or for 10 seconds. See if you can say anything at all about the policy. Isaac, talk with Jennifer and Cindy. Jennifer and Cindy, talk with Isaac, please.
Why would C come back? Oh, because it'd be 0. Yeah.
Okay, who can tell me anything? Who can tell me one thing about this Vena?
Okay, so at the point 0, 2,
Yeah.
the slope of the function p is 4.
Okay.
And since the second derivative is a negative function, the function itself would be concave down, right? So it would go like this.
I don't want you to say that.
Okay.
No. Concave down? Okay, later. Yeah.
Yeah, would it
Okay,
go like
so it's true that what you're saying is right, that the second derivative tells you about the rate of change of the first derivative, right? So the first derivative there is 4, and the second derivative is -7. So that means that the first derivative is decreasing,
Yeah.
right? So the slopes afterwards are gonna be
Less.
decreasing, right? So you know that it's gonna be sort of curving like that, right? So that maybe gives you some information about. That's good, right? That gives you some information about the polynomial, right? Like that tells you in particular something about A, right? What does it tell you about A? A is negative, right? Because you see that this thing is curving, so that's good. Yeah, that's good. You see this thing is curving, and you know it's a parabola. If it's curving like this, it's got to be curving downwards. Okay, so you know that A is negative. Okay. Julian, yeah. C is 2, right? Great, right? How do you know it? Just plug in 0, right? You know that P of 0 is 0 plus 0 plus C, right? It happens to be 2, so you know that C is 2. Great. Okay. Right. Can you do that? Can you do that with? What about? Did you stop there, or did you go on? Did you go on more? Said B was 4. Okay, let me think about it. P prime of 0 is 2ax plus b plus 0, right? Evaluated at 0, so x is 0. That gives you b, right? So b is 4. Right? So c is 2, b is 4, right? And what about the last one?
The last one will be 2a equals
2a.
equals
Great. Right. So P double prime of 0, right? You see you get 2ax evaluated at x equals 0. So I'm sorry, you get 2a, excuse me. So 2a equals -7, and so that tells you that a is -7. So you can figure out, everything. What do you know about this polynomial? You know everything about this polynomial. Right? You know exactly what it is. Right? P is going to be -7 halves x squared plus 4x plus 2. And so you can sort of see what could happen. Suppose if you knew all the derivatives, right? Suppose you knew, you have some function, you have some polynomial, and you know, like, if the polynomial is of degree 10, if you had up to the 10th, derivative evaluated at 0, you'd still be able to figure out exactly what that polynomial is in exactly the same way. Any questions? Okay, so this is the beginning of something called scalar Taylor polynomials, which you'll see more of next term. Okay. Okay, so that's all I want to say about this section. Let's go on to 3.8. Something called the method of implicit differentiation. Okay, so here's the example problem. So somebody gives you a circle of radius 2, x squared plus y squared equals 4. A circle of radius 2, and they give you a point on the circle. The circle is, so right here, this thing is -3, -1. So here's a point on the circle, -3, -1. And they ask, what is the slope of the tangent line what is the slope of the tangent line to the circle at that point, -3, -1. So they want the slope of the tangent. Okay. How do you find the slope of the tangent line? Anybody? How do you find the slope of the tangent line? By taking the derivative, right? The derivative of what? Of some function, right? So what's the function? If somebody said, take the derivative of the relevant function, take 10 seconds and write down the function that you have to take the derivative of. What's the function for this part here? Okay, so what's the function? Sarah? Yeah. X squared plus y squared equals 4? Is that a function?
Or would be oh, so it would be the section
That's okay, Elise?
The square root of 4 minus x squared.
Okay, yeah, right. Y is square root of 4 minus x squared. Is that right? That's almost right, but can somebody fix it up a little bit? There's one thing that's missing. Negative, right? Because we want the lower half. We said the square root of 4 minus x squared, we get the positive, so we want the negative one. Right? So we realize that this thing, y is actually a function of x. What function is it? You solve for y, realize it as a function of x. So method 1, this is what we can do at this point. Solve for y as a function of x and differentiate. Okay. So y is negative 4 minus x squared to 1/2. You differentiate that, right? Think of y as a function of x, right? You differentiate it, and what do you get, Marcella, when you differentiate this? Negative.
oh my god, 1/2 4 minus x squared to the negative 1/2
Right. So by the chain rule, right? Use the chain rule. Differentiate the outside guy, which is blah to the 1/2, right? And then multiply and evaluate that at the inside guy, and multiply that by the derivative of the inside guy. So you end up with x over the square root of 4 minus x squared. Okay, and so that's the derivative of the function, right? And how do we get the slope here? We just plug in, right? We just evaluate that at x being negative root 3. So y prime at negative root 3. Leave it down here. Sorry. Y prime at negative root 3 is going to be negative root 3 over the square root of 4 minus negative root 3 squared, and so we get negative root 3. So that's one way to do it. Everyone, any questions? Luke? No, yeah.
So in order to find the slope, you just plug it into the equation and differentiate.
So what we did was we got a function describing this lower half. Right? That's this thing. We realized from the equation we got a function that describes the lower half. Right? Then, right, how do you find the slope of the tangent line? The derivative. Right? So you take the derivative. And you evaluate it at x equals negative root 3. Right? So you take the derivative, right? We get the derivative, and then we evaluate the derivative at negative root 3, and we get that the slope is negative.
And then for that, when you do the chain rule,
Yeah.
the chain rule is because you got x beside, so formally is 2x, and
That's right.
Okay.
Right? Because you've got, you have this outside function which is something to the 1/2. Right? When you differentiate that, you get 1/2 blah, right? So blah to the 1/2. When you differentiate that, you're going to get 1/2 blah to the negative 1/2. Right? So you get 1/2 blah to the negative 1/2, but then you have to multiply by the derivative of the inside. What's the derivative of the inside? Well, it's going to be 0 minus 2x. Right? 0 and then minus 2x by the power. Okay, so now method 2. Okay, so this one is a little bit trickier, or a little bit more clever. You say, well, you assume that y can be realized as a function of x. Right? So you think x squared plus y as a function of x squared equals 4. You think, well, y really is a function of x. As x changes, y changes. Right? Assume, or in this case, really observe, that y is a function of x, right? Y depends on x. Y depends on x. Right? And so you just write this thing as x squared plus y of x squared equals 4. Realizing, incorporating your realization. Okay. And then differentiate. Differentiate that thing with respect to x. Okay, and what do you get? Well, what's the derivative of 2x? I mean, x squared is 2x. What's the derivative of this part? Somebody just tell me. So 2y of x, y prime x. Okay? By the chain rule again. And then you've got something squared, you differentiate the outside guy, you get 2 of y, and then you need to multiply by the derivative of y. And then the derivative of 4 is of course 0. Okay. So what we're doing is we have a relation between x and y, and we differentiate it to get some relation between x, y, and the derivative. Okay. Now look what that gives you. We can we divide the whole thing through by 2, right? Multiply both sides by 1/2. We get x plus y prime equals 0. Right? And then solving for y prime, what's y prime?
Wait, did you differentiate it?
Nope, I just divided by 2. What's y prime then? Negative x over y, right? Negative x over y. Okay. So now, what's our point? So our point was negative 3, 1. So I'm going to put it over here. Our point, right? So what we have is that y prime x is negative x over y, right? So at the point of interest, what do we have? Y prime is then going to be what? Negative 3 over negative 1. Right? In other words, negative 3. Cool. Right? Okay, so you start off with this relation between x and y. You realize y is a function of x, differentiate it, and you get a relation between x, y, and y prime. Solve for y prime, you get y prime in terms of x and y. Well, we were given x and y, right? So just evaluate it there, and you can figure out what y prime is. So we didn't have to solve for the function. Right? You don't have to solve for the function. You can just start from, right? You don't have to take the square roots and stuff. You just start from the equation, differentiate it, and then solve for y prime. Okay? And that's called implicit differentiation. Okay, so you don't create a function and then differentiate that function. Right? But you just differentiate the whole thing and then solve for y prime. Okay. Just out of curiosity, which one do you like better? Who likes number 1 better? Okay. Yeah, good. There's no right or wrong to this question. Who likes number 2 better? Okay. Yeah. So okay. So let me ask you to do one for exercise. Okay. Yeah. Here we go. Xy squared plus yx squared equals 6, and the point is 1, 2, and I want you to find the slope of the tangent. Okay, so it's almost the same sort of problem. It's exactly the same sort of problem. So you see that this one would be a real pain to do if you tried to solve for y, right? If you wanted to solve for y, well, it's going to be a little bit tricky. Yes. Yes.
X over y is negative x, right?
It was negative x actually,
Oh.
right? Because you got what did you get? y prime equals negative x, move the x to the other side, and then divide those sides by 1. Okay, you turn to somebody nearby and say what you are doing. Okay. Colton, how about you? So, first thing you do is realize, describe the y as a function of x. And then what do you do? So we'll differentiate the whole thing. And what happens? What rule do we use? Okay, but watch out, right? You've got two functions here, right? So you want to use actually the product rule first, right? And the power rule will come into it in a second. So you take the first guy times the derivative of the second guy. Now you use the power rule. So what do you get? 2yx times y prime x, right? So you have to differentiate everything. So that's the first guy times the derivative of the second, plus the derivative of the first guy, that's just 1, times the second. Okay? So that's, we've differentiated this thing. Now we differentiate this thing. What do we get? Say it again?
Would it just be 1 because you can't do it?
No, I mean, again, we're going to use the product rule. So you take the derivative of the first guy, it's going to be y prime, times the second guy, times just the second guy. So, and then the first guy, well, that's just y, times the derivative of the second guy, 2x. And then we differentiate 6, well, that's it. Okay. Okay, so then we have this thing, and you could solve it for y prime, or let's just plug in at this point. Okay, I mean, we'll just plug in for x and y at this point. So let me write it out. We got 2xy y prime plus y squared plus y prime x squared plus y 2yx equals 0. So all I've done is removed the dependence. Okay, I'm just sort of abbreviating. Right? You get this, and let's just plug in x is 1 and y is 2. Right? So x is 1, y is 2. We get 4y prime. Y is 2. So we 4 here, x is 1, and x is 1, y is 2, you get this. Okay. So 5y prime equals -8, and so y prime equals -8 this. Did I make a mistake? It's possible.
I don't know if it's specific, but
Okay.
in the very first, one down, yeah, how did you get the lowest?
I get 4y prime because I'm substituting in x is 1 and y equals 2. Right? Our point is 1, 2. So x is 1, y is 2, and I get 4y prime.
So that's when we plug in the points.
Yeah.
Is this,
At this point?
yeah.
Yeah, you could, or if you wanted to, you could solve for y prime first and then plug in. But in this case, I think it's easier to plug in first and then solve for y prime. It makes 0 difference. Any questions? Well, this is pretty cool, right? You can get the slope of the line, even though calculating the function itself here would be, a little bit painful. Can I erase? Okay, so there's one last trick, which is finding higher derivatives using this method. Okay. So I'm going to do a simple example, and I hope that this will be enough for you. So xy4 plus x equals 17 at 1, 2. So we're going to find, say, y double prime at 1, 2. So what you do is you say, well, okay, I'm going to think of this as a function of x. Okay, and I'm going to differentiate. And I get the first guy times the derivative of the second guy. Plus the derivative of the first guy times the second guy. Differentiate this x, I get 1. Differentiate the 17, I get 0. Okay. And so, I can calculate for y prime. You get 4xy cubed y prime plus y to the 4th plus 1 equals 0. Right? And substituting in 1 and 2 gives me 4 times 8, 32, right? 32y prime plus 16 plus 1 equals 0. And so y prime is -17 over 32. So at that point, at 1, 2. Okay. So far, all we've done is the same thing as we did before. What's the question, Luke?
I'm just a little confused how you.
The fruit of 32 comes.
Oh, because you do 3 times 4.
Yeah, so this is 2 cubed, that's 8. Right? Y is 2, x is 1.
Oh, you plugged in.
And just plug it. Plugging in. Okay, but the question was to find y double prime, right? So how do we find y double prime? Well, we're going to have to take this thing and differentiate this to get some statement about y double prime. Okay. So let's do it, right? You take, let's take, this is the first guy. So you take the first guy, times the derivative of the second guy, plus the derivative of the first guy, right? Well, that's going to be the first guy times the derivative of the second guy, plus the derivative of the first guy times the second guy. Right? So first guy times the second guy, plus the derivative of the first guy times the second guy. And then we need to differentiate that, so we get 4y cubed y prime, and the chain rule, plus 0 goes in. Yeah, Elise.
So, what about is the purpose of this like, the first one is the differentiation, but
It doesn't have such a good graphical representation.
okay, it's more about the
Yeah, that's it. It's acceleration. Yeah. Okay, right, so you get this, so you differentiate this thing, right? We started from here, differentiated and got this, right? We can use this to solve for y prime. We differentiate this, right, and we get this thing, right? We get this thing, and this is a relation between x, y double prime, and y prime, right? Right? So you just plug in, right? X is 1, y is 2, and y prime was negative 1732. Right? Negative 1732, and then solve for y double prime. Right? So you're going to end up, do you want me to do it? Let's not do it. So you just solve, right? It's arithmetic after that. So but you can use implicit differentiation to get higher derivatives in this manner. Okay, that's it for today. Again, if you want some candy, feel free to come up and take it. What? So for homework, this will be 3-7 and 3-8. 3-7 and 3-8, because 3-7 was that very short.